Welcome to another episode of Spike's Science Spot. This episode is all about the technology of measuring length and distance. You might be thinking, how is a ruler technology? Stay tuned and find out. The definition of technology is anything created by humans that makes our lives easier. In our journey together, we've often talked about observations. We make observations to learn and to discover things new to us. We often need to compare our observations, so we take measurements. For measurements, you need to have standards and units. One of the first units of length was called the cubit. The standard for the qubit was based on the human body. The qubit was defined as the distance from the back of your elbow to the tip of your longest finger. Thousands of years ago in Mesopotamia and Egypt, the common unit was the cubit. Here you can see everyone's qubit is a little different in length, causing all sorts of measurement problems. You can imagine people were frustrated by the variability in all of these measurements. In 1793, France decided to use the Earth as the basis for defining a new unit of length called the meter. The meter was defined as 1/10,000,000th of the distance from the North Pole to the equator going through Paris, France. In 1983, the standard for the meter was improved by defining it relative to the speed of light, a universal constant. Now you see that a ruler is an improvement in technology from the qubit. All the tools you see here make direct measurements of objects, just like a ruler. An indirect measurement is when you're measuring something by measuring something else. For example, measuring length or distance on a scale, map, or drawing. How do we measure objects that are really big? A building, a tall tree, or a mountain? I know I don't have a tape measure long enough. We need to use indirect measurements to determine the height of a building, a tree, or even a mountain. Surveyors, civil engineers, and construction engineers use indirect measurements to determine distances and elevations when laying out highways and tunnels and bridges. In this example, to find the height of a tree, we measure its shadow and the shadow of a known object. For details of the shadow method and other methods, use the link to go to our website. Give one of these methods a try on a tree, building, or mountain near you. How do we measure a distance that's even bigger? For example, like the distance to a star. To measure distances to stars, we use something called parallax. Parallax is the difference in apparent position, sometimes called the displacement, of an object viewed along two different sight lines. Another way to understand parallax: take your thumb, hold it at arm's length. First cover one eye and then the other. What did you observe? To me, it seemed like my thumb was moving, but actually, in one instance, I was looking at my thumb, from the location of my right eye, and the other time I was looking at my thumb's location from my left eye. Now let's try it maybe with your thumb closer to your face. Cover one eye and then the other. What did you observe? And how was it different than when your thumb is held all the way out at arm's length? This diagram demonstrates how we make two observations from the Earth that are 6 months apart. Knowing the distance from the Earth to the Sun and the parallax angle, we can use trigonometry to calculate the distance to an object in space, like a star. Again, for really big distances, we have used an indirect measurement. Hello, Dr. Imelda Atencio. Welcome to Spike's Science Spot. Please share a little bit about yourself, maybe what your job is, what you studied at university, and if you always knew you wanted to study lasers and optics.
Thank you. I am I'm Dr. Atencio, as she said, or you can call me Dr. Imelda. A lot of people like to call me that. And I'm actually from northern New Mexico. So I grew up in a really small town in northern New Mexico where there was barely one little street light. And so it was really, really dark. And I would spend hours outside with my binoculars because I couldn't afford a telescope and looking at the stars. And I loved astronomy. And so my goal from when I was about probably 5th grade-ish time frame was to sit on a mountaintop with my telescopes. And that was my goal. I was going to be an astronomer and sit on the mountaintop with my telescopes. And when I went to New Mexico State University for my undergraduate down in Las Cruces, and they started a program called electro-optics. And I said, ooh, I like optics. And it was a program where it was crossed between physics and engineering. And one of my professors pulled me aside one time and said, hey, you're really good at, it was called geometrical optics. Have you considered becoming an optical designer? And I said, cool, what is that? And so I really owe professors. But during that time frame, I also realized that my gifts, I'm much more of an engineer. I tinker, I like to mess with stuff, take things apart, put them together. I like to figure out how things fit. And so I wanted to become an optical engineer. I found out that that was a thing and go into optical design. And I didn't know how I was going to get to grad school, so I came to work for the Air Force Research Lab. They sent me back to school at the University of Arizona in Tucson at the Optical Sciences Center, where I got both my master's and PhDs. So I thank the Air Force for that. And now I want to tell you, I achieved my dream. I spent almost 19 years at a facility called the Starfire Optical Range here on Kirtland Air Force Base in the foothills of the Manzanos for about 19 years of my career, having a blast. So sorry, that was a little bit longer than I intended, but.
Well, wow, thank you. That was very cool to get your biography there. So we've been studying and learning about measurement, especially length and distance. So our question for you is, why do we want to know how far away objects in space are?
Well, if you are, as I said, I really loved astronomy growing up. I really wanted to know where I was in the solar system and in the universe. And so many people are like that. So they develop ways to measure and figure out what our solar system is like, and figured out that we actually have elliptical orbits and not circular orbits. And that's all done through measurements and math. We start looking at stars, well, how far away are those? And we devise different measurement techniques to figure out really what is going on in the universe. What are there other solar systems like us? Are there other galaxies? What are they all? What is all that? And we have found and we have figured out that the universe is expanding by doing these measurements. And we figured out where we sit in our solar system and in the galaxy. So it's really kind of cool. So measurement in a lot of sciences is very useful and a fundamental part of research.
Okay, so we've talked a little bit about using parallax to measure the distance to some relatively nearby objects in space. Are there other ways other than parallax to measure distances?
Yes, there are. For nearby, you can use lasers or radar. And what's really cool about that, if you may or may not know, but there's a mirror on the moon that I can't remember which Apollo mission put that there. I think it was one of the later ones. And I've actually was part of a experiment one time where we propagated a laser out of our telescope facility at the Starfire Optical Range, bounced it off that mirror, and got it back, received it. And so what you do is you timestamp it. You figure out the exact time that it left and the time that returned. And so now you have basically what we call the time of flight, to and fro, and you know the speed of light. And so you can figure out what that distance is. So what do you do when you're even further out? Well, then you can use the parallax for closer stars, like Spike has taught you here. There's also, if you're going way far out, it's called the Doppler Shift or a red shift. And so I'm sure all of you have been near a train track at some point in time, and you hear the whistle blowing way in the distance. As it gets closer, the pitch changes. So the frequency is a little bit higher, and then it goes back off and it wanes away. Well, the same thing happens in light, because that is a frequency as well. It's just a visual. We see a red shift. It pushes towards the longer wavelength. And so you can measure that and get distances from that. Hope that covers it, Spike.
Yeah, that was great. Thank you, Dr. Imelda. We appreciate your time. Thanks for coming to Spike Science Spot.
Thank you so much, Spike, and hope all the kids out there enjoy it.
We have explored measurement units and standards. We learned to use indirect measurements to measure things that are really big. So if you want to keep exploring, I suggest you investigate how to measure things that are really small, like a grain of sand, or the width of one strand of hair, or one single bacterium. How are those things measured? So keep exploring, keep observing, and share what you learned at hashtag SpikeScienceSpot and hashtag AFRLNMSTEM101. See you next time.